All right, let's resume our discussion. Recall that we are in the network flow, and we sort of work through an algorithm we designed, and then we are sort of in the middle of trying to prove the correctness of this algorithm. And in order to do that, we need to first establish a very important mathematical theorem, that is the max flow and mean cut theorem, right? So last time we were sort of at the what's called the flow value lemma, and let me just move to a cleaner page, right? So this value lemma says that if I have a network flow, right? So this is a flow network. Sorry, this is a S and this is T. And now let's just chop this network into two halves. Let's call the left hand side is A, and let's call the right hand side is B, right? Now the flow value lemma says that if I really look at two islands, right? So look at the island A and island B. I look at all the flow that are circulating from left to right. And then I also look at all the flow that are circulating from right to left. Then basically I can sort of claim that the left to right flow minus to right to left flow is exactly the value of the flow, right? So what this literally is saying is that if I want to count the amount of water or liquid I can push from S to T, I can directly calculate the value of the flow. Basically, I can focus on the node S and look at how much flow that's circulating out of S and subtract this amount by the amount of flow that's circulating back to S, right? So this is the definition of the value of the flow. But in order to calculate the value of the flow, we can also utilize any cut, right? So let AB be any cut. And in order to calculate how much water that's moving from S to T, I just need to calculate how much more water that's moving from A to B minus the amount of water that's moving from B to A, right? So all the water, so basically if you assume that there are 10 units of water moving from left to right and the 5 units of water moving from right to left, that basically means that there are exactly 5 units of flows that are moving from left to right. And all these 5 units of flow can only, right, where can you start from? You can only start from S, right? And where can you end at? You can only end at a T, right? So when I subtract these two numbers, I get 5, and 5 would exactly be identical to the value of the flow, right? That's the high level intuition of how can we use an arbitrary cut to calculate the value of a legitimate flow, right? So, and here that it is a rigorous proof of the correctness of this lemma, and then we did that in the last lecture. So, in case you want to review, you can just go back to the last lecture's video and look at how this is proven, right? So now we finished on this flow value lemma. So there's another closely related lemma that's called the weak duality lemma. So basically it says that the value of the flow is less than the capacity of the A and B, right? So let's really just compare like the difference between these two lemmas, right? So let me just try to cut this out. Let's see whether I can copy and paste. No, I can't. No. Let's see whether I can copy and paste. Let me see. Copy, and let me paste that. Right. So let's say that so what I want to do is really to compare these two lemmas. The first lemma says that that's the flow value lemma, right? And this is the weak duality lemma, right? So the right hand side, they remain the same, right? The left hand side, right? So originally when we talk about the flow value lemma, it's really focusing on the flow itself rather than the network, right? It's about how much flow I'm using for each of the edges that's going out of A, and how much flow I'm using for each of the edge that's going into A, right? But for the weak duality, this becomes a capacity, right? So really the left hand side is a fixed flow. The right hand side would be something that's irrelevant to the flow, right? Your plan, how do you plan to push water from the source to the destination? It's the structure of it's related to the structure of the network itself, right? So that's the capacity, right? So the weak duality basically says that for any feasible flow, its value will not be larger than the capacity of any cut, right? So AB would be still like you can just pick up an arbitrary cut, right? So now we can briefly walk through how this can be proved, right? So this here is how the entire procedure to prove the whole weak duality lemma. As you can see, it's a pretty short one. So let's just go through the arguments one by one, right? The first equality basically is really just the flow value lemma, right? So this is directly coming from the previous result, right? From the previous slide, right? And from the first one to the second one, what we are doing is that we are just eliminating the second term, right? The second term, right? So all the flow has to be positive. When you sum up a set of positive number, it will be a positive number, right? So when you just decide to not subtract a positive number, so that's the reason there's a less than equal to here, right? So this is out of A. Right, so from the second line to the third line, it uses the fact that the flow of an edge is at most as large as the capacity of an edge, right? So this is what we are using, right? So it has to be, basically we are using the fact that the flow has to be a feasible flow, and in case it's a feasible flow, it cannot be larger than any edge. If I look at the flow value for any edge, it cannot be larger than the capacity, right? And after I calculate, I get the E out of A, and the capacity of all E is basically, if you look at the definition of the capacity, right, that's exactly the definition, right? So the weak duality is also pretty straightforward. The value of the flow will not be larger than the capacity of the cut, right? So we also mentioned that there's an island, right? So if you look at you remember that 2 lectures ago, like we sort of say that if I'm a very powerful monster, I really cut the island into 2 pieces, I only need to look at all the bridges that are moving from at the left to right and see the capacity of all the bridges sum, right? That would be a bottleneck, right? So this weak duality is exactly characterizing the intuition I mentioned 2 lectures ago. Right. So the weak duality itself is pretty straightforward. There's another straightforward corollary coming out of this weak duality. This is so-called the certificate of optimality. So basically, the certificate of optimality, let me just talk a bit about the high level idea here, right? So a lot of cases when we want to be able to tackle an algorithm problem, usually the first question is not even trying to design an algorithm to directly solve the problem. Instead, you ask that even if I come up with a solution, is it possible to verify the correctness of the solution efficiently, right? So for instance, if you talk about the sorting, right? So imagine you have a black box, and that helps you to do the sorting on the array. And in order to verify the correctness of the black box, it's actually pretty straightforward, right? So whenever you feed an arbitrary array into the black box, and then black box claims it's able to sort the array, and then you look at the output of the black box, and then you examine the elements one by one. You want to make sure that the next element is always larger than the previous element. If this property holds for the entire array, then it's sorted, right? So sometimes when you face a problem, actually it's pretty straightforward to verify that the whether a black box can completely solve the problem, right? But sometimes things are a little bit less trivial. For instance, if I ask you to solve a shortest path problem, and say for instance I ask you to help me to find a route coming from Williamsburg to New York City, right? So somehow the Google Map or the Dijkstra algorithm or whatever black box that's claiming that is able to solve this problem gives you a path and route that helps you to move from Williamsburg to New York City. Then there's always a question that how can you verify this is an optimum solution, right? So in fact, it's actually much less trivial to verify the optimality of a path, right? So it's very difficult to verify that a particular path connecting between Williamsburg and New York is in fact the shortest path, right? So basically, in order to verify that, you probably also still have to run an Dijkstra on your own and then check that it's indeed because the Dijkstra is correct, and indeed that the output coming from the black box is also correct, right? So just now we examined the two examples, right? The first example is the sorting, right? So in order to verify the correctness of sorting, right, the verification is actually easier, right? Easier than the solving the problem on itself, right? So if I just want to verify whether black box gives you a correct solution, it's called the verification. The verification is straightforward. And then I also mentioned about the shortest path, right? Shortest path is actually it's much less trivial, much more subtle, like in terms of when we compare the complexity of the verification versus the complexity of the solving the problem. So it's actually not clear the verification. It's easier. It's easier than the solving the problem, right? So the corollary right here is really just says that in case we are trying to solve an optimum, trying to find the optimum flow in a flow network. In fact, there's actually a way to certify the optimality of the problem, at least like if certain condition is met, right? So this is the significance of the corollary, right? The corollary is, let's move back to this corollary. The corollary says that if F is a flow and AB is a cut, in case the value of the flow is the same as the capacity of the cut, then we can claim two things. The first thing is that F is a max flow. The second thing is that the A and B is a mean cut, right? So basically, so that the corollary says that in case value of the flow is the same of the capacity of the cut, we can certify optimality of two things. The first thing is that F is optimum. It's optimum in the maximum flow problem. The second thing is that A and B is optimum. The optimum in the mean cut problem, right? So let me go back again. Like let me just make some more additional comment. So about why do we want this kind of certificate, right? So the very, very major reason is that like before even trying to come up with a solution, you sort of even want to know that, okay, in case I'm able to find the solution, am I even able to verify that correctly? Or sometimes it's very difficult to do that. Then you can sort of just know that it's actually coming up with a solution can only be more difficult than that. So let me also give you an example in which finding the certificate is difficult. For instance, if I want to make a claim that Alice is the tallest female student in the College of William and Mary. So now, in order to certificate that this statement is true, there's not too much things I can do, right? So I really have to walk through every single female student in the campus and measure their heights and then make sure that they are shorter than Alice, right? So yeah, so if I need to convince you this statement is true, then I need to pull out the statistics of every single student in the college to tell you that now there exists no such a student that's taller than Alice, right? So so this is an example in which certifying one statement is very difficult, even that's a true statement, right? So in general, it's true that if you want to prove something doesn't exist, it's actually very difficult. For instance, if you submit your homework like in paper form, you submit some hard copy of your homework to the instructor in some of the courses, and then instructor couldn't find your homework, and then if you make the claim that I indeed submitted that, right? So it's going to be very difficult for instructor to say that otherwise, because if instructor want to prove that the homework, you never submit the homework, you never did the homework, basically he or she is effectively trying to prove that something doesn't exist. And in order to prove something doesn't exist, it's very difficult, right? So this kind of certifications of optimum solution or certifications of a specific statement, right? How much effort is needed to certify a specific statement. These kind of things are going to be discussed further in the intractability chapter, right? That's actually one very center notion in theoretical computer science. But for now, we just need to walk through this corollary. As I said again, that if somehow we manage to find the value of the flow is the same of the capacity of a cut, then we know that both the flow is maximum flow and the cut is minimum cut, right? The proof itself is pretty straightforward, right? So in case we pull out, let's pick up any arbitrary flow f prime. So value of f prime is going to be less than or equal to capacity of A and B. That's the weak duality we did just now, the weak duality. And for the second equality, it's really just the equality that's given from the statement, right? So the capacity would also be the same as the value of Vf, right? So if you look at the first term and the last term, basically it's proving that value of f prime is at most as large as the value of f, right? So this is for any flow f prime, right? So basically this is the definition of the value of f is optimal, right? Similarly, for any cut A prime, B prime, so capacity of A prime, B prime is at least as large as the value of F, right? Because of the weak duality, right? But value of F would be the same of the capacity of A and B, right? So this is what's given, right? So if I look at the both ends of the inequality, again, I get the capacity of A prime, B prime, is at least as large of capacity of A and B, right? So that's basically the definition. A and B is a mean cut, right? So, but the entire corollary is built on top of the assumption that if the value of F is the same as the capacity of A and B, right? So, are we able to find such an F and such an A and B? The corollary didn't state anything that's giving us useful information, right? So in fact, just from this corollary, we cannot tell, right? But as we can see next, the strong duality basically says that we can always find an F and a cut A and B such that the value of the F is the same as the cut, right? So that's basically the statement of the strong duality. So let's really just proceed, right? So this is the original paper on the flow problem, right? So this is actually the paper that's written almost 70 years ago, right? So now let's move to the max flow and mean cut theorem, right? So basically, as I mentioned, the value of the max flow is the same as the capacity of mean cut, right? So basically, what we did just now for the weak duality basically says that the capacity of any cut is at least as large as the value of flow, right? So that the less than equal to this direction is the same. It's the easier direction we have proved, right? So now we sort of want to prove that the other way. Right. So the other way, basically, we want to prove that the value of the flow of max flow is also larger than equal to the mean cut. Right. So this is what we need. Right. In order to prove that, basically, this is the major building block we need to prove the whole theorem. So let me just erase everything. So this is the major building block we are going to argue. Right. So a flow F is a maximum flow if and only if there exists no augmenting path, right? So basically, the augmenting path, right, it's a notion that's sort of introduced in the Fulkerson algorithm that we discussed about last time, right? So we are going to review that very soon to just recap what is that, right? But the theorem basically says that there's a way to verify that whether there's a max flow, right? We just look at the residual graph and see whether S and T's are connected, right? And then by having this, after we get this augmenting path theorem, then we are able to show that the max flow is the same as the mean cut. And in fact, we are going to prove the equivalence of all these three conditions. Let me just explain that to you, right? So if I pick up any flow, right, for any flow that's feasible in the network, right? So the equivalence of this all three conditions means that if one of the condition is true for this particular flow, then the rest of two conditions, the rest of two conditions of statements are also true, right? So for instance, if I pick up an arbitrary flow F and such that I can also find and cut A and B such that the capacity of A and B equal to F, if that I'm able to do that and making the statement 1 is true, then basically we also know that F is at max flow and there's no augmenting paths with respect to F, right? So that's the meaning of the whole statement here, right? So similarly, if somehow I notice that the F is a max flow, then I also know that I'm always able to find card A and B such that the capacity of A and B is the same as value of F, and similarly, the third statement is also true, right? On the other hand, if I know that, right, one of the statements is wrong, right, so I pick up an F, I know that F is not a maximum flow, the second statement is wrong, then basically I also know that first and third statement are wrong, right? So that's the meaning of the meaning of the equivalence, right? So if I pick up any flow F, either all these three statements are true or all these three statements are wrong, right? So I don't think that the slides is going to help us to review what's augmenting paths, but let's really just briefly review that, right? So let's recall that we have let's just draw that we have a very small flow problem as T, and let's call this A, right? So, and let's also write down the current usage of the flow, right? So let's say 6/17 basically means that the capacity of the edge coming from S to A has 17, and for the current flow, it's using six unit of flow, right? So if I want to make the flow look like a real one, I need to change the one here, right? So again, like if I look at the second pair of number here, 6/10, that basically means that if I look at the edge that's connecting from A to T, the capacity is 10, and the current flow is currently we are using 6 unit of the capacity, right? So I need to change this to 6 from A I wrote just now, just to make sure the flow conservation property holds for A, right? So this is a legitimate one, right? So if I pick up an arbitrary one, so let's just recap what's the residual graph. Right, the residual graph, right? So remember that we were sort of drawing this kind of things, right? So if there are something going towards one direction, right? So, and then we use the 7 unit of the a total amount of 10 unit of capacity, then the residual graph we are going to build is from A to B, I'm able to push 3 units of flow. From B to A, I'm able to push 7 units of flow. 3 here comes from 10 minus 7, and 7 here, really, it's really just a replication of here, right? So this is what we call the residual graph, right? Right. And similarly, if I want to compute the residual graph for this for this particular instance, is really just as moving from A, I still can push 11 units. From A move to B, from S it's 6, A to T is 4, T to A is 6, right? So this is how we are going to get everything out of here, right? So this is 4 and this is 5, right? So this is the residual graph, right? Right? And augmenting paths basically says that within the residual graph, am I still able to find a path that's connecting between S and T, right? So this is the augmenting path. Like if I'm able to, so basically, so let me just write that down. So for that's any path that's connecting from S to T in the residual graph. That's called the augmenting path, right? So basically, let us just reinterpret this whole theorem, whole statement, right? So basically, it says that if F is a max flow, if I look at the residual graph, S and T's are disconnected, right? So this is basically this is what statement 2 and 3 are about, right? So now I think we don't have any questions in interpreting this result, what the statement is about. So now let's really just go ahead and prove the statement, prove the results over here, right? So we want to prove that all are equivalent, right? So what we need to do is to prove that 1 implies 2, right? This is our first part, right? And then we want to prove that 2 implies 3, right? So this is our second part, right? And then we want to prove that 3 implies 1, right? So this is indeed what's all are needed. All these 3 parts are needed in order to prove that all these 3 statements are equivalent, right? So when we say that we want to prove the equivalent, they are equivalent. This is the one possible approach to execution plan to prove the equivalence, right? So now this is exactly what the slides is trying to execute, right? So the slides still first tries to prove that one implies two, right? So one implies when we want to prove one implies two, that basically means that if one is true, then two is also true, right? So this is what we want to prove, right? So when expanded, that basically means that if exists A and B such that this equality holds, let me just change the color a little bit, so such that this equality holds, then that implies F is max flow. Right. So this is abstractly what we need, right? So if one is true, the second is true, right? If we unfold the statement of 1 and 2, right? And then we want to get out what we really want. Basically, this is the statement, right? So if there exists A and B such that the capacity of A and B equal to the value of F, then we know that F is max flow, right? So let me just not to try to move things. Let me just directly write that, and such that capacity of A and B equal to the value of F, right? So this is what we need to prove, right? So when we say that one implies two, we want to prove one implies two, that basically this is what we need, right? So and the lecture slides really just says that in order to prove that it's really just the weak duality, let's see whether that's true, right? So if exists A and B such that capacity of AB equal to value of F, right? So that's exactly the weak duality we were talking about, right? So weak duality is the corollary, so, right? The corollary exactly says that, right? If there exists an A and B such that value equal to A and B, then F is a max flow, right? So basically from 1 implied 2, basically this is just a repetition of the weak duality corollary, right? So now, the next thing we want to do is that after 1 implies to 2, then we also need the 2 implies 3, right? 2 implies 3 means that what we need to prove is that if F is max flow, then there exists no augmenting path. This is what we need to prove, right? So in order to prove that, what we really just want to prove by contrapositive, right? So in case there's an augmenting path, right? So I want to negate the third statement, then we can improve the value of the flow, right? So contrapositive basically means, let me just repeat, if we want to prove by contrapositive, we really just want to say that if exists augmenting path, then F is not maximal, right? So this is what we want to prove, right? If we manage to prove that, that implies that we can prove 2 implies 3. But this is exactly, right? So as we mentioned in our algorithm, right? In case we look at the residual graph, right? So if this is a residual graph, and then I'm able to find a path that's connecting from S to T such that there are some capacity along every single edge, right? So there are some capacity alongside every single edge. None of the edges is 0, right? So in case I'm able to find this augmenting path, then I'm able to sort of add an additional flow on top of the existing one, right? Which also means that F is not optimal. F is not maximal, right? So basically, this is really just coming from the definition of the algorithm we designed, right? So in case the augmenting path exists, we can always do improve, right? So 2 to 3 is also straightforward, right? So if you look at the actual substance, what's even stated here is exactly the same as what we said just now, right? So suppose there's an exists and augmenting path, right? So that's with respect to F, then we can really, by sending flow along this path, right? So we can really just send a little bit extra flow along this augmenting path, right? So now when we modify F and get some better flow, that's also feasible within the same network, that basically implies F is not max flow, right? So 2 implies 3 is also pretty straightforward. So at the end, we want 3 implies 1, right? 3 implies 1 means that we want that if there's no augmenting path, right, that basically implies what's the number 1, right? So exists a cut such that A and B, capacity of A and B is the same as the value of the flow, right? So this is what we need, right? So, and actually this is actually the most difficult part of the Prime-Module theorem.